The learning objective and this, so after we complete this module, you are supposed to be able to understand the difference between program and the process. Understand the process state. Process can change state during execution. Including developing programs using the appropriate system calls. Usually, we will focus on fork, create a child process. So we want the child process to execute different program and wait, sleep, exit the system calls. So first is a concept. Process concept. So what is a process? Execute a variety of programs that run as process. So that before this class, we always say program. The computer, the operating system execute a program and we run a program. Memory, this program is called process. A process is a program in execution. Process is an active entity corresponding to the program after this program has been loaded into memory and is being run by CPU. So the process is a program in execution. It is an active entity. And the program is a passive entity stored on hard disk. A passive entity. We write the source code, for example, the main.cpp. This is our CPP program file. And but this is a CPP file. The computer cannot execute this file. So if we want to run this file and we need to compile this file, we use a G+ to compile this and -o main. So the compiler, the G++ compiler compile main.cpp, compile this source code file and get an executable file main. So the -o means we want the executable file named executable file name as main. Now we get executable file main. This is still our program. And now the main.cpp source code file disk on our hard disk. They are programmed. They contain now in the .cpp ++ statement has which statement if else the variables. But in the main, in this the machine language instruction 01 machine language instructions are all programmed. If we want to load executable program memory, if we want to run this executable file, we use, or in the GUI, we can double click this executable file to execute this file. And in the command line, we can type this /main to execute this executable file. So after we type this command, run this program, or we double click this executable file, it's loaded in memory. So this program is loaded in the memory and it process. it becomes a process. This program is loaded in the memory, stored in memory, becomes a process. So now the main, this is a program. The passive entity stored on our hard disk, secondary storage, and it contains a list of machine language instructions. One is, and then when load this program in memory, it becomes a process. And now in execution, it is an active entity corresponding to executable file. After this executable file has been loaded into memory and is being run by CPU. A program becomes a process when an executable file is loaded in the program started where GUI, mouse click, or command line entry of its name. So now we run this program, and this program is loaded in the memory, becomes a process. Now in the Linux, we can use the shell command to see the current running process. I will show you this. Now I use PuTTY to connect to the Linux lab.
Sorry, Professor. I think it for me yesterday when I'm logging, it takes a lot of time.
Yeah, sometimes the network is not good. Even
You connect to the VPN.
on campus, I use a campus network. So yeah, need the VPN. Okay. We have the shell command PS to show all the processes. Now, first we check the manual page of PS. That is PS. PS report a snapshot of the current processes. Different option. to see every process on the system using the syntax PS-E, PS-EF. We also process tree because the process we have the last lecture we know the when the power is off, there's no operating system in the memory. So when the power is on, the operating system loaded from the secondary storage to main memory. And a small program called the bootstrap. This small program it is in the BIOS in read-only memory. This small piece of program know the location of kernel or the operating system on secondary storage. So the CPU runs the operating system from the secondary storage to main memory. And then the operating system will start the first process. The first process is system D. Now, we can process is a system D. And this process can create other processes. Other processes are child of this process. And also the process can have the child process. And then we have a process tree. We also can use this command to print out the process tree. Now, I will see the main page, the PS. Okay. This command shows the process related to this. There are only two processes. Now, if I type the process for PS-EF, it will show all the processes in this. Two. Now we can see we have many processes. Now let's take a look at the process. PID is a process ID. The first process is a system process. And now the PPID, this is the parent process ID. Parent process ID. Now we can see process the RCUGP. This process, the child of his thread, the child of this process. We can see this one. This is the RPC. This process is the child process of system D. This is the processes. And show the dynamic real-time view of running system. Now it will show now this process use the CPU 8.3% and use the memory, use this memory and its process ID and the user name. And now I also can see student use this one. Other students are using the same BB350. This is the top. Now, the top, this process is running. If I want to exit this process, if I want to terminate top this process, I type the Control-C. Okay, this is a top. Now, okay, I will run the top again. Now I tap the top, I run this, let's just. Top is a user command. It displays processes. Now, for this process, so top is a shell command. It's when I type this command and press enter, it becomes a process. Now, if I want this process run at background, I can add the ampersand. Okay, now I will show you the difference. Now, I didn't add the ampersand. So means this command run in the foreground. If I type other, now I type other command, so there's no response because top is running and I type any command, I cannot interact with the computer. But now I terminate, to terminate this process. Now I use a top and the ampersand. If I add the ampersand, means I want this process run at the background. Now you will see the difference. Now the top is running, but we can type the other command. But now the top is PS. Now we can see top is still running at the background. Now, let me see. Okay, I will show you another command. Well, true. True. Oh. Word. Done. And now I run this while loop. This while true do echo hello world done. So this while loop is always true. Okay, now I will add one more thing here. Sleep. Okay. Now this while loop is always true. So that means we will print out hello world and then sleep. So stop and pause for 10 seconds and print hello world and then pause for 10 seconds to do this loop forever. Now, if I run this script command back, so now I will foreground. Okay, now we can see the hello world. And now if I type the other command, we cannot get print out any result. Okay. And then I terminate this while loop. Okay, now I terminate this while loop. Now I run it again. I add the ampersand. Ampersand means I want this while loop from background. Now the while loop run at the background. Now I tap the shell command. I can get the response. But now after 10 seconds, while loop still print out the hello world. Okay. After 10 seconds, it print out the hello world. And then, let me see. FG means so foreground. Now, after I type the command FG, this FG is a foreground. Means I want this while loop to run in the foreground, not the background. After we put this while loop on, now I type the PS, there's no response. Okay, now the hello world at the foreground. Now I can use a Control-C to suspend it. Control C means the this while loop. Suspend this while loop, this process still in the system. I use the PS, we can see the while loop sleep, it's still in the system. Still in the system. Okay, it's still in the system, but it's a yeah. When I type FG, this while loop resume the execution. Okay, now I will use a Control C to terminate it. So Control and Z means to suspend a process. The process is still in the system. And the Control C means that we terminate a process. Now I tap the Control terminate while loop. Now I use PS. Now we can see the while loop is not here. Some command, the process command with some command related to processes. So you. One more thing is I want to see this PS tree. So we know the process. We have many processes, and the process can form an upside down tree. The first one is a system D. First one, this is the root is a system D. This is the first process of the operating system loaded in the memory. And then the system D create all these child processes. And the child process can still have the child process. Now, here we can see this child process has this child process and child process. So we have multiple level, this process tree. Now, let's go back to the lecture notes. Process information. When a process is loaded in the memory, this we call the process image. This process image contains multiple parts. So it has so-called the text section. It contains the machine language instructions. And then so when we use global variable. Global variable is a variable we declared outside of any functions. So global variable are stored in data section. And then we have heap. Heap is a part of also belong to the data section. And the heap, we also store data in heap. And the heap contain memory. What is a dynamic variable? Dynamic variable in the C++. C++, we can use new operator to declare dynamic variable. Now I use a new operator to declare dynamic array. This is a dynamic array. So we can use variable to set the capacity of this array. Now this array is stack. Stack contains temporary data related to functions. Main function and the main function called other functions. This function information are stored in stack. Example, the variable we declared inside the function is called the local variable. Local variables are stored in stack, and we have the parameter passed to function, and also the return address of the function. These are all stored in the stack. So when the main function is running on the CPU, the main function has it's called the activate record at the stack. So every function has an activate record at stack. We will talk about this when we will talk about this again at memory management. Now the process in the memory from this is the maximum memory address, and this is a 0. Now the process from the address 0, we have the text segment, store the codes, machine language instructions. So we call a function, and it's here, and we declare variable here, and we have the addition operation z equal to x plus y. They're all right here. The instructions, machine language instructions are right here. And then data at so I will say above or after the text section, we have data section. We store the global variable in the data section. So in fact, these are all called data section. So because in the heap we also store data. So but now in this section we store the global variable and the static variable, and in the heap we store the dynamic variable. And then stack we store the function called related information, related data, the local variable, the return address, the function parameters. Now this is a 4-part of a process, but here we can simply draw the arrow here and also the arrow here. The stack start from the maximum address. Let's see the logical address, the maximum logical address. Now, when the stack grows, the address decreases. And when the heap grows, so the heap grows towards stack, and the stack grows towards the heap.
Thank you.
Okay, so now this is a how a process is stored in the main memory. How the process is stored in the main memory. Okay, so now any questions for this part, process concept and the process in memory? The process state. The process execute it. Process is an active entity, so it has different state. It changes state. It has this 5 state. First state is new. New process is being created. So when the system after system initialization, the new process is created. System D, and the system D create other processes. And the user process request. So now as a user process, we can call the system call to create child process, create the new process. So we will talk about fork this system call in detail. So the process is new state. And another state is ready. Ready means the process is waiting to be assigned to a CPU, waiting to be assigned to a CPU, and process get all the resources except CPU. So this process already get the memory and get the input output devices, the file, open some file, and it get all the resources except CPU. So now the process is ready to be selected and dispatched to CPU. So this is ready. And now okay, so now this shows how a process can be ready. So a process can change from new to ready. And a process also can change state from ready. And also can change from locked to. We will talk about this later. Now we just know that ready means the process get all the resources except CPU. The process is ready to be attached to a CPU. The running the instructions, the machine language instructions of this process are being executed on CPU. So this process is running on the CPU. When a process is ready, this process is selected and dispatched to the CPU, and this becomes ready. So this is running, and then blocked. Blocked is also called blocked waiting. So it's also waiting, but in this course we call it blocked. Blocked or waiting. Blocked or waiting, this state process is blocked and waiting for some event to occur. So for example, when a process is running on the CPU and this process requests input-output operation, need to read some data. So now this process is blocked because this process need to wait, need output operation to complete. So the blocked, when a process make input-output request and wait for input, this process will be blocked. And when a running process needs some resources, but these resources are not available, so these resources are occupied by other processes. So the current running process is blocked. Or the running process wait for child process to terminate, the current running process is blocked. So the blocked process only can change from running to blocked, not from the ready to blocked, only from running to blocked. And then the last terminated means the complete process has finished execution. So now a process can exit normally, or the normal exit, the process terminate, or there's some error, the access the invalid address and division, so the trap, and the process terminate, or the process is killed by another processes. So we have we type the control Z. Okay, no, we type the control C to stop this process, to terminate this process and kill the process. We also have the system call to kill a process. Okay, now this is a how the process change state during the execution. Now, first we have the process is new, and then it get all the resources except CPU. It becomes to ready. So from new to ready means the process get all the resources. Already get the memory, get the devices, get the files, open files. So it's ready, except CPU is ready. And when a process is ready, it can change state to, okay, when a process is ready, we can say it only can change the state to running. So now when a process is ready, and the scheduler select this process and dispatch to CPU. So this process changes the state from ready to running. Here in the multi-programming system, we may have multiple ready processes. Okay, we have multiple processes in the memory. Now, at the time, we can have multiple processes already. Okay, now we have 4 processes, they are ready. Now the operating system, we have a component called scheduler. The scheduler will select a process. Okay, this, for example, the scheduler will select this ready process. So this process is dispatched to process, change the state from, okay. Yeah, this is the process change the state from ready to running. When a process is running, that means the CPU is executing its machine language instructions. So fetch instruction. So the CPU read the instruction address from the register PC, fetch this instruction, and then the ALU execute this instruction. So the use the fetch execute cycle to run the instruction of this process. Now the process is running on the CPU. And now we can see its state can change to ready, can change to terminate, can change to blocked. So now the three possibilities. Now change to ready, change to exit, change to block. Now let's take a look at running to terminated. From running to terminated, it's easy. We can have the normal exit, or we can have some error. This error will cause the program to terminate, cause the process terminate, and the process is killed. So now this 3 and the process can change from running to terminated. Okay. And now from running to blocked, from running to blocked, we can see when put out operation. So we know access in devices is very slow. For example, waiting for the user input from keyboard, it's very slow. So now this process is blocked, waiting for the user to enter a letter, or the input from the keyboard. So the process is blocked. Input output operation. And is the running process needs some resources some resources, but this resources is available. So it needs some resources, but this resource is not available. So now the current running process has to release the CPU because the current running process needs some resources to continue, but these resources are not available now. So the current running process is blocked. And now the next one is a wait for child process. I will just write the wait for the child process. If the current running parent process and this process cannot complete, this process need to wait until the child process complete, and then the parent process can complete. So we will see this example next lecture. So for these three events, when a process is running on the CPU, if these events occur, one of these events occur, this event can block the current process, or we say the current running process will be blocked because of this event. Okay. Now this is running, change from running to blocked. Okay, we have this from running to ready. When a process is running on the CPU, it also changes the state from running to ready. To ready, this happens when the now we know we have the time sharing system. Time sharing system is means we have multiple processes in the system and switch among these processes. So the process 0 uses CPU for a time slice for 5 nanoseconds, and then process 1 uses the CPU for 5 nanoseconds. So these processes, they take turn to use CPU. Now, okay, when the process 0 is running on the CPU, one time slice, 5 nanoseconds. So the time slice expires. After 5 nanoseconds, this process is not terminated. It's not finished, or it still has instructions. So now the time slice expires. This process has to release the CPU. Now the time slice expires. It will timer interrupt. Send the timer interrupt. This timer interrupt will change the process state from running to ready. Means this time slice to release the CPU, and now the next process will be dispatched to the CPU, run on the CPU. So this is how they take turn to use CPU. Not one process use the CPU forever until it terminates. So this is one thing is when a running process runs the CPU for one time slice, and this process not terminated, process change state from running to ready, and wait for to run. Next time it dispatched to the CPU. So this time expires. Another situation is when a process is running on the CPU, and now we have a new process arrives at the ready queue. This new process has a higher priority. Okay. The higher priority process the new process with a higher priority arrives at the ready queue. Because this new process has a higher priority than the current running process. Now the running process has to release the CPU. Change process with a higher priority will be dispatched to run on the CPU. Okay. This is two events. These two events can change a process state from running to ready. Now this is a run to ready, blocked ready. We know this a process can be blocked because of input-output request sources and wait for child process. Now, if this event occur and the input-output operation terminate, the input-output operation complete, and this resource are available, and the child process complete, and this event completion can move a process to ready. Okay, now a process waiting for the user to enter a string, and now the user enter the string, the input-output operation complete. Now the process get the user input. This process change the state from blocked to ready. So the same thing. And now the process, for example, process waiting for a resource, this resource occupied by other process. Now the other process source. Now the blocked process can get these resources. So the blocked process change the state to ready. And also a parent process waiting for the child process to complete. The process terminate, and then the parent process change the state from blocked to ready. Okay. Now this is how a process can change state during the execution. This diagram is very important. So you may see this in the midterm exam. Also, here's some we will concept. So for the time slice and for the process with higher priority, see this concept when we talk about CPU scheduling. And for the need resource, we will see this when we talk about synchronization. Yeah. Okay, now this one from ready to from running to ready. From running to ready. Now we can see from running to ready. This is a to this to the previous two pages. Well, the process is ready. Ready means it get all the resources. The process change from running to ready. Ready. The first two, this means a change from running to ready. And then the third one means change from blocked to ready. Means change the block to ready. Change from block to ready. occur, the input output complete, the child process complete, and the resource are available. This event so can change a process from blocked to ready. And then locked. These three events process change from running so when these three events occurs, one of these three events occurs, it can change a process state from running to blocked. Okay. Now, one more thing is a process cannot change the state from blocked. We don't have. So a blocked process cannot. This is invalid. This is invalid. Okay. A blocked process has to be ready and then dispatched on the CPU. And this is also important. Now the process contain all these informations, process ID, process state, and also the process name, and it also contain the information. These information are all stored in process control block. This is data structure, PCB, process control block. Process control block store the information associated with each process. It's a state, ready, running up. It store the program counter. So what is a program counter? PC, it's a register information. It's a register. In this register, the location of instruction to next execute, or we say we store the address of the instruction. So now when this process is dispatched to run on the CPU, then it's stored in register PC. And now the CPU will start instruction. And also the other CPU registers in the process control block, we store the other CPU registers informations. For example, memory information and the register. Register store the memory address allocated to this process. And we also store the CPU scheduling. For example, the priority of this process. This process, if this process is in the ready queue, there is a pointer point to the next process, ready process. If this process in the queue, there is a pointer point to the next blocked process. And the memory management means the memory allocated to this process. This information stored in process control block. And accounting since start and time limit. And also the and input output devices allocated to this process and list of open process are stored in process control block. Each process has a process control block. All of them maintain this process control block. It create a process. Operating system will create a process control block for this process and maintain this process control block. Now some example of the process control block. We have the register, PC, and the status, status and the stack pointer, process state, priority, and the process ID. Every process has a unique process ID in the system. Every process has a process ID. And also they have the parent process ID. Parent process ID, also the process group. So some information about the CPU time used, and the memory management and the file management all stored in process control block. In fact, it depends on the operating system. Now in the x86, it's a very simple process control block is very small. So we will take a look at x86 next week. So we can see it's just contain the part of these informations. It has a process ID, parent process, and the process state, and also process name and user. Yes, I think we don't have the memory management information stored in x86 process. We will take a look at it next lecture, next week. Yeah, different operating system, they may have different process control block data structure. Process scheduling. Two very important component. One is called the scheduler. So the scheduler among available processes for next execution on CPU core. There are multiple processes, they're ready. They're waiting for CPU. So the scheduler will select one process and will dispatch this process to CPU or to CPU core. So now the selected process changes the state from ready to running. Okay, for the process scheduling, select a process to run on the CPU. The goal is to keep CPU busy all the time. So we keep CPU busy all the time, CPU utilization. So we aim to quickly switch processes onto CPU. Process 0 run on the CPU. When process 0 is blocked, process 1 is dispatched on the CPU. Process 1 run on the CPU. Process 1 is blocked. Process 2 is dispatched to run on the CPU. So we want to keep CPU busy to maximize CPU utilization. So we have the multi-programming system. That means we have multiple processes in the system, so we can keep CPU busy. Now the process behavior, the general behavior of a process are described as a input-output bound or the CPU bound. The input-output bound. The input-output bound process spend more its time doing input-output operation than doing computation. So now some processes, they are input-output bound. So they use more time on input-output operation, less time on computation. So less time on the using CPU do the computation, more time to do the input-output operations. So the input-output bound process. And another type of process behavior is a CPU bound. CPU, we use this process use more time to do the computation, use the CPU to do the computation. Then to make input output request. So this kind of process, they make input output request infrequently. So they use more time doing computation. Scheduling queue. The operating system need to maintain scheduling queue of processes. We have the ready queue and the blocked queue. The ready queue processes residing in memory, ready and waiting to execute. We have the ready queue. When there are multiple processes, they're ready. The system put this ready queue, put this ready processes in a ready queue. And the blocked queue or the waiting queue, blocked queue contains a set of processes blocked and waiting for an event. So we can have multiple processes, they are blocked because of some event. So they are all in the blocked queue. Processes migrate among the various queues. So when a process, let's go here. So now here we have the ready queue. Ready queue. These are all process control blocks. Now, assuming in this ready queue, we have 4 processes. 4 processes are ready. And now blocked queue, we have 5 processes. Some of them are blocked because of the input-output operation. Some are blocked because of the child process. So now the process 0. Process 0 is blocked because of the input-output operation. When the input-output operation complete, the process 0 move from blocked queue to ready queue. Now, when the user input terminate, just get the user input, this process is moved from the blocked to ready queue. It gets the needed data to move to the block to ready queue. Now, in the ready queue, we have 5 processes, and in the block queue, we have 4 processes. Okay, and now, assuming this is the process 2 is selected to run on the CPU, the process 2 is removed from ready queue, and the process 2 run on the CPU. Process 2 run on the CPU. If the process 2 request input-output operation, process 2 is added to the blocked queue. Wait for the input-output operation. Okay. Change like a process, they move the difference between these queues. Now this is an example of block queue, the ready queue. Here, this is a linked list. This is a process control block. Now this process 7's process control block. It contains all the process information, and it also contains a pointer pointed to the next ready process. The next ready process is the process 2. So now here we have a head pointer onto the first process control block, and we also have the tail pointer point to the last process control block. This is an example of the ready queue. The below one is a blocked queue. So the head pointer pointed to the first process control block in the ready queue, in the block queue. And the tail is a pointer pointed to the last locked process control block in the list. Okay, so far, any questions? Some information about the processes, concept of processes and process state, how the process change state, and the process control block and the process scheduling. We have the ready queue and the block queue process, migrant.
One question, Professor.
Mhm.
If the program in this loaded in the RAM, but is not in the execution, is not a process. No, means
Okay, you mean when a program is loaded in the memory, it's a
yes.
state is not running. So it's it's in the memory. So it get the memory resource, but it's not to get it still don't have the required the CPU. It cannot get the CPU. So it's loaded in the memory ready. It's ready. And now when the scheduler select this process, dispatch this process. But now when we load a program in the memory, when we type the ./me, it seems like because the access speed, for us, we think it's very fast. But now for the CPU already changed I think at least processes. So run the output process and the context switch, and then run your main run immediately, but it's not. It's not, and the operating system code are running on the CPU and then switch to the user process.
Okay, thank you, folks.
Welcome. Okay, we will talk about the context switch next week. Talk about the fork, how to quit the child process. And the assignment 1 due by next Tuesday. So please before the Tuesday, if you need any help, it's our on Monday morning from the office hour. This is office hour information. It's our Monday 9 to 10:30. This is Zoom meeting. And Tuesday from 12 noon to 12:50.
Thank you, Professor.
Bye.
Bye.